In this unit, we'll be talking about Lewis structures. Welcome to our second video. So the octet rule, or some of my students in the past have called it the suggestion, and you'll see later why, is that atoms tend to gain, lose, or even share electrons until they have 8 valence electrons. This makes them as stable as noble gases, which is kind of their goal, to actually be in a stable configuration. A common way to represent covalent molecule structure, as in how they bond or react to satisfy the octet rule, is the use of Lewis structures. So when drawing Lewis structures, the following steps are going to help you. I will say, some people do this different way. If you've been taught a different way and that works for you, go ahead. This is just a step that works for me, so I'm going to help you with it. Well, hopefully help you with it. So, step 1. Sum up all the valence electrons from all the atoms in your structure. Okay, we've talked about valence electrons before it goes off the group number. For example, H2O, we're going to have 1 times 2 plus 6 from oxygen times 1 to get you 8 total. Also, CO3 2 minus would be 4 for carbon plus 6 from each of the oxygens. And because we're actually having a 2 minus charge, that means we've taken 2 electrons. So that gives us 2 more for a total of 24. Vice versa for NH4 plus. That'd be 5 plus 4 minus 1 because we lost 1 for a total of 8. So anyways, sum up your valence electrons. That is step 1. Alright. Step 2 is write the symbol for the atoms. Now, not only are we writing the symbol though, we're also connecting them with a single covalent bond. So for example, if we're doing H2O, we would do this as H, O, H. Or for CO3, 2 minus, this would be O, C, O, O. Now, the biggest question people ask me are, how do you know what goes in the center? Why aren't they all just one straight line, etc., etc.? There's 2 main things I can tell you. First off, hydrogen is always on the outside. Okay? Secondly, if that doesn't solve every issue, then the atom with the lowest electronegativity is typically going to be in the middle. Most often that's going to be carbon. As you can see up here, that's oxygen. But mainly in this part, you actually have hydrogen can't be in the middle, so that means oxygen has to be. And here, we've got carbon in the middle. Hydrogen on the outside, lowest electronegativity typically in the middle. And if all else fails, you'll normally have one element and like 3 or 4 of another element. The one with the least amount tends to go in the middle. You just kind of get a feel for it as you keep working. Alright, step 3. Complete the octets around all atoms bonded to the central atom. Now, that means do the ones not in the center first. Okay, remember they want 8 valence electrons. Hopefully you remember that hydrogen's fine with 2, which means once you actually put a covalent bond to hydrogen, leave it alone. It already has 2, it's being shared. So, that also means, though, that you are placing electrons out around the central. So, you're taking electrons from step 1 that you tallied. I forgot to mention that every time you write a dash in step 2 for covalent bonds, you have to subtract 2 from your total, because a single covalent bond is 2 electrons. And then, basically, you just start putting pairs of dots around until every atom gets 8. So, back to H2O. Hydrogen's on the outside. We don't need any other valence electrons here. However, we originally had 8, but since we put 2 bonds out, that means we're down to a total of 4. And for CO3, we had a total number of electrons of 24, because we had 2 minus. We put 6 bonds out, that gets us a total of 18. And if I were to fill the actual octets around the outer atoms, we would end up needing a total of 18 more, which would get us down to 0. Now, that's actually going to be an issue in a bit, but we're okay for now. So, there you go. That's the first 3 steps. Step 4 is place any leftover electrons on the central atom. So, for H2O and CO3, for H2O, we had 4 extra electrons left. we now place those 4 on oxygen. Now, fortunately, that actually fills oxygen octet. We have 2, 4, 6, 8. We're done. For CO3 2 minus, we have a slight issue because we did not have any extra electrons. So we don't place any more on carbon. We'll come in and adjust a bit to what we actually do in this situation. So 5. If there's not enough electrons to fill the central full octet, like in carbonate, try stronger bonds. Well, let's go back to that. We currently don't have any more electrons. That means we need to try stronger bond, which means instead of just sharing 1 pair of electron, we share 2 pairs. So what you do is you pick any atom that has currently a full octet but is bonded to something that does not have the full octet, in this case, any of our oxygen, and you're going to take one of its pairs and move it to the middle. So, for example, let's take this pair and actually move it in here. So we would actually take this, move it here, and thus we would actually write a double bond. So, notice there's only 4 non-bonding electrons on oxygen now, but it still has 8, and now carbon has 8. We could have done that with any of these 3. It doesn't really matter. We'll talk later about which one we should pick, if it actually matters. But now, everyone actually has a full octet. Yay. So finally, if the compound is a polyatomic ion, like carbonate, we write its formula in brackets with the charge in the top right corner of the bracket. So, for example, on this compound, we would actually write this as 2 minus. So that just shows that basically all this is only possible if we take 2 electrons more than we would normally start. Alright. So, go ahead and draw the Lewis structures for the following molecules. I'm going to let you practice, then I'll actually show you what the final answers are going to look like. Alright. These are our 4 Lewis structures. Hopefully you're able to get these. If not, consult the actual guidelines from before that I showed you. You'll be able to get them. So, if we find that we have multiple correct Lewis structures that differ really only by how we placed our electrons, we can call them resonance structures. So back to that carbonate, when we could have picked any of the different oxygens, we would have called each, basically each structure that we used, if we put the bond on a different oxygen, a resonance structure. And we indicate resonance structures by drawing a double arrow between each one. That shows that basically these are all basically equivalent, if you will. So, try to draw both resonance structures of ozone, so 3. Come back in a bit and I'll show you the answers. Alright, here's our resonance structures. Now I know it really doesn't seem that big of a deal, just changing the actual bond location. That will come in handy a little bit later, but that's kind of our point, is that there are multiple correct answers and we need to actually address that. Because the bond can come in handy later, just make sure that when you're drawing resonance, you put the arrows between them. Alright, thanks for watching. That's Lewis structures.